Hi, I'm Sam Bentson at Aprovecho Research Center. I want to tell you about measuring firepower while cooking so that you can determine the ISO 19867 tier weightings. We'll be doing that using a total capture emission sampler. We measure firepower while cooking so that we can report a single thermal efficiency or any other metric available in the standard. We measure performance at high, medium, and low firepower. So we report the performance at high power, medium power, and low power. And then we do a weighted average based on the amount of time that was spent cooking at each of those power levels. And then in the standard it says, disclose the method that was used to determine how often the stoves were used at a given power level. So now I'll show you how to use the total capture hood to measure the time resolved firepower while cooking. Now you've seen the LEMS in the laboratory, and now here we are in front of the pemS. The pemS is a portable emissions monitoring system. We're taking the same type of measurement. We've got a rocket stove, and the rocket stove makes smoke, and the hood captures all of the smoke from the stove. The smoke travels up through the hood and into the dilution tunnel. Just like the LEMS, the dynamic pressure inside the dilution tunnel is measured, and the temperature inside the tunnel is measured. With those two measurements, we measure the total volume through the hood. Then we have the gas sample line and the real-time PM 2.5 sample line going to the new sensor box. And we have the gravimetric system, the same particle separator, the same filter holder, going to the now portable gravimetric system. The sensor box and the gravimetric system have been integrated into one portable unit. It's set up in front of the LEMS because it can still be used to measure the real-time emissions from the cook stove. And it can still be used to collect the gravimetric sample of PM 2.5. It uses the same gas sample line, the same pressure sensors, the same computer interface. We're looking inside the system now, and here's the sensor that's used to measure the flow rate through the gravimetric system. There's space for another unit so that during LEMS measurements, when two filters are used, we can measure the flow rate of both. This system doesn't use a critical orifice to control the flow rate. It uses a needle valve. So that's something that's not optimized for laboratory use. It's optimized for portable use. This valve doesn't take as large of a pump to operate, but it requires more frequent calibration. One of the capabilities of the sensor box is it has an expansion port. What we have set up here at our lab is with two thermocouples, and this one has been configured with an oxygen sensor. So we've expanded the expansion board in the new sensor box. This one's set up for one flow sensor, two flow sensors, a carbon monoxide sensor, with more to come. The system is powered by the grid, and we have the laptop to view the real-time emissions and to store the data. For 16.7 liters per minute, these pumps and this flow controller, they draw 50 watts. The rest of the sensors draw 7 watts. As a point of comparison, the pump for the gravimetric system for the LEMS draws 230 watts. This fan draws 150 watts. This fan and these pumps can be operated off a large battery, but at 1,000 watt hours, the best use case is a grid-tied hotel near the village. I want to show you the travel cases, the sensor box and filter system fit in this box, and you can carry it that way. And the hood and the dilution tunnel fit in two of these boxes. Without the gravimetric system, you can use the the 3000 series sensor box, then you don't need this box. You only need 2 of these. The reason why we test cook stoves at multiple fire powers is because there are many cases where with increasing firepower there's increasing particulate matter. So I have a graph here with particulate matter and time elapsed, and then the gray line is firepower. And so here were test results when we were cooking. It was a different stove, but they were both open fires. The other advantage is that when you're watching somebody cook, you can see where some of these emission spikes come from. In some cases, you can see here firepower increased PM, but in this case it was the opposite, maybe because the fire went out. So it doesn't always happen like this, where higher firepower, higher PM, but there are many cases like this. The way we measure firepower while cooking is we capture all of the CO2 and all of the CO. The particulate matter can be used, but it's based on the amount of carbon from the CO and the CO2 emissions rate. There's some in particulate matter, but it's such a low mass that it doesn't contribute very much. And so then we derive the carbon burn rate, and I'll show you the equations to convert to firepower. The next thing we do is we correct the firepower that we measure in real time using the carbon balance. So that's when we compare the amount of carbon that was emitted in the emissions, the amount of carbon that we measured, versus the amount of carbon that we think is in the fuel. So now let's take a look at those equations. We have the carbon emissions rate and the mole flow rate of the CO and the CO2, the molar mass of carbon, and we have power based on the carbon measurement. So here's the same variable. Here's this carbon fraction of the dry fuel that we need to measure, and the lower heating value of the dry fuel needs to be measured. In the standard, there's equation A9 uses this notation for carbon balance in a little bit different way, but it works out the same, where there's the total amount of carbon measured divided by the total amount of carbon burned. So here's those equations. Then what we do a little bit differently is we have the firepower from carbon, and then we multiply it by this value. So that allows us to correct based on moisture content, and if there's a change in energy content going from wood to charcoal, we can correct this way. It also works for leaks in the hood and fuel is not weighed. There's other ways to do the calculation, but this is an approach that counts for more than one error at once. So once you've measured the firepower, then the spreadsheet will count the amount of times that each one of these measurements fits in a bin. So you have to define the firepower bins, and then the spreadsheet puts the power in the bin. The spreadsheet counts how many times each power went in the bin, and you end up with the weighting factor. So then you put in the weighting factors in the ISO water heating test spreadsheet, and then it gives you these performance metrics that are weighted based on the measurement that you made during the CCT. So finally you can get one thermal efficiency for the stove and one CO per energy delivered to the cooking pot and 1 PM per energy delivered to the cooking pot. That works really well when you just want to say this is the performance of my stove and get a simple answer. The new sensor box that you saw along with the pemS was developed for the Rwandan Bureau of Standards. I had the good fortune of going there this summer, and here's Bernard Caveira, the lab manager there. Thank you for your attention.